Assalamu alaikum wa rahmatullahi wa barakatuh. Hello, members. This is me, Sheikh Zedan. And firstly, I would really like to thank the I- ICSPC 2024 IEEE 12th Edition Conference on System Process and Control for allowing me to present my paper, which is on design analysis of the effect of trimmable vertical stabilizer for enhanced aircraft maneuverability and directional stability. Hello, members. This is me, Sheikh Zedan. I graduated bachelor's in aeronautical engineering from MBJ College of Engineer in India, Bangalore, and currently pursuing my master's in aerospace engineering at King Fahd University of Petroleum and Minerals, Saudi Arabia. My key interests are to develop the CubeSats, CanSat, and work on lightweight helicopters and light combat helicopters. My current research is on CubeSats and space applications. I'm very keen to pursue a career in aerospace field and contribute my works towards exploring aerospace innovation in order to ensure productive work. Moving forward, today's agenda is to introduction, objective, literature review, problem statement. We'll discuss methodology, we'll discuss physical design, design philosophy, validation, results, and the paper outcome and the conclusion. So friends, we all know that aircraft plays a vital role in our day-to-day lives. We all know if we want to travel anywhere or we're going anywhere and we use for long distances, we basically use the aircraft. But there is a problem. Sometimes what happens is due to high wind or due to high gust, which is traveling from the side or the crosswind, which in technical terms of aerospace, the aircraft is are not able to land usually, and the pilot feels difficult during these stages. It is harder for the pilot to land, and the aircraft will not be landed on the runway. So, what happens in these cases? The pilot takes a turnaround or go around and come back and retry to attempt the landing. But sometimes, due to this, what happens is the fuel consumption is more, and due to which sometimes the aircraft cannot fulfill its requirements. So, we have come up with an idea where we talk about TVS. And what is TVS? TVS is trimmable vertical stabilizers. Yeah, an aircraft vertical stabilizer, which we all know is a vital part in vertical tail, which is useful during a high wind, during landing, which regulates the movement of the aircraft and preserving the stability when flying in high speeds. Today, our goal is to study, which is presented in our paper, is to use a traditional robust control technique to design a thermovoltaic stabilizer, enhancing the aircraft control moment, efficiency, maneuverability, and direction stability, which is proposed, but the TVS operates as a single system that permits the whole vertical tail movement. We have also used a simulating-based simulations to confirm and validate the suggested control schemes. The analysis focuses on the determining the angle of turn of the aircraft under particular flight conditions and analyzing how the TVS affects efficiency. This study of ours advances the understanding of using a robust control algorithm to create sophisticated aviation control with potential implications for increasing overall aircraft performance and study. The objective of our paper is to contribute and serve as an academic tutorial to learn and understand the usage of the classical robust control algorithm to create sophisticated aviation control system. During our paper, during our research, the problem statement and the challenges we faced is the challenges in design and simulating Trimmable Vertical Stabilizer (TVS) for an Airbus A321-200. This is a model which we have taken and will be working on it and will be calibrating all the results. The study highly talks about the complexity in designing the trimmable vertical table stabilizer. We'll be designing it, requiring advanced stability and dynamic considerations due to the absence of rudder. Here, in place of rudder, we'll be modifying it and making as a trimmable vertical tail stabilizer. The simulation difficulties arose in applying the trim angle accurately, compounded by limited references and validating data for comprehensive, comparative performance analysis with conventional vertical tail stabilizers. Moving ahead, we have gone through many literature reviews, but I'll be explaining six of them, which are very essentials, which are very important. The first paper is robust nonlinear dynamic inversion control system to improve the stability of large aircraft in crosswind. The author name are M.I. Babar. Year of publication was December 2020. And the inference in this paper describes of the flight stability and control system along with original and improved lateral response of large aircraft in crosswind as experienced during landing. Coming to the second paper, which talks about the experimental analysis of aircraft directional control effectiveness, the author was F. Nicolosi and D. Calibriti, which was in the year of November 2020, and the inference talks of the control surface on low aspect ratio lifting spacecraft exhibits different lifting capabilities compared to those with a high aspect ratio. Moving forward, the fourth paper talks about the quantitative weight and two particle search algorithm to optimize aero stealth performance of the backward inclined vertical tail. The author are Zizo. Year of publication is April 2023, and the inference talks about the reduction of air drag index in obvious, and the optimal solution appears to be the boundary and the backward tilt range. Coming forward, the next paper talks about the aircraft direction stability and vertical tail design, a review of semi-empirical methods. The publications are the authors D. Calibrity, P. Della. Year of publication is November 2017. The inference talks about the conventional semi-empirical technical techniques commonly utilized for estimating the direction stability. Derivatives in preliminary aircraft design are notable for their original in wind tunnel experiments, predominantly conducted on earlier flight aircraft configuration for earlier decades of 20th century. Lastly, the paper which we went through was a performance enhance of the vertical tail model with sweeping jets. The author was J. Danzui. Year of publication is December 2020. The inference talks about the active flow control to delay the flow for separations on the rudder of two different models has been which was investigated on Onera LI wind tunnel. Coming to the design philosophy, we all know as a part of an initial phase design for the Airbus A321-200, which is shown in the figure, it was modeled and drafted in CATIA V5. For this study, we use a symmetrical aerofoil section, which is of NACA 0012 from the aerofoil tools for vertical tails and have a thickness ratio of 12% to accommodate a wide variety of angle of attacks. Coming to the methodology, here you can see the parameters are vertical tail span, vertical tail mean chord, vertical tail area, center of gravity of aerodynamics, center distance, and Reynolds number. These parameters are essential for determining the stabilizer's aerodynamic performance and directional stability. The Reynolds number of the airfoil indicates the flow regime. Is calculated on the tail. The vertical tail stabilizer parameters includes as shown in the table. The design of the vertical tail of the conventional aircraft like Airbus A321- is large and higher in that can cause more positive movement, contribution, directional yaw, and static stability derivative of the aircraft itself. The geometric modeling. The NACA 0012 airfoil modeling, which we used, was modeled using ANSYS workbench, using coordinates from airfoil tools with control volume and fine mapped mesh creates for aerodynamic analysis. The discretization meshing, which is the second procedure after we have modeled the from ANSYS workbench, we meshed it and discretized of NACA 0012 aerofoil ANSYS fluent, which is used to disguise the control volume into a smaller elements for accurate results. Each part is meshed individually and the aerofoil input-output were defined to ensure the optical flow formation. The element size was 0.005 meters. Coming to the state space model and PID controller, the MATLAB code is generated to simulate the yawing motion of the aircraft using the state space representation, which defines the physical parameters such as wingspan, velocity, air density, and moment of inertia, and which creates a state space model based on these parameters. The total torque is determined by various factors, including the aerodynamic drags. The formula is L is equal to minus CD rho by 2 AV square psi, where L is the represents the yawing moment or the torque due to aerodynamic drag force acting on the aircraft. CD here refers to the drag coefficient, which depends on the shape of the aircraft, its orientation of the airflow. Rho, the air density, which directly affects the aerodynamic forces. A represents the typical related to the aircraft wingspan or the cross section that interacts with the airflow. V square talks about the aircraft velocity relative to the surrounding air, the drag force increasing quadrilaterally with velocity. Psi is the yaw rate of change of angle, or the correction factor or the projection parameters related to the yawing motion. The state space model was developed in the MATLAB to simulate the yawing motion of the aircraft. The state space representation is defined by the following equations, which are used in our paper. Here, x of t is the state vector, e of x is the input vector, y of t is the output vector, and a, b, c, d are the system matrix. Why we use PID? PID control is applied to stabilize the yaw and roll motions of the aircraft. The proportional integral and derivative gains were turned to maximize the deviation in yaw rate under sinusoidal disturbance. The simulation is used, which is used to state the space model to evaluate how the trimmable vertical stabilizer responded to the control input and external disturbance, improving the aircraft overall directional stability. The simulation results are discussed based on the model which we have created. The CFD simulation is conducted using the ANSYS Fluent 2024. The meshed aerofoil was analyzed at various angles of attack to plot the lift coefficient CL and drag coefficient and varying boundary conditions to mimic their realistic flight scenarios. The angle of attack were of 8 degrees and which was computed for the lift coefficient CL of 1.2368 while the values for drag coefficient was CD 0.01729. These controls helps to visualize the airflow pattern, demonstrating the increasing the aero angle of attack, increase the pressure disturbance, the pressure difference between the aerofoil upper and lower surfaces. Simulation using OpenVSP software and XFLR5. Apart from ANSYS, we have also used the simulation software, these two simulation software, to check our results. Here in the first diagram, you can see that the trimmable vertical stabilizer, which is analyzed using the OpenVSP, where the figure below shows that demonstrates the pressure coefficient disturbance and aerodynamic forces, along with vertical stabilizer, mean aerodynamic chord section. In the second diagram, you can see the wing body combination, mid-wing configurations, where the fuselage mounts up to 10% of the vertical stabilizer causing streamline to be slightly deflected, impacting the stabilizer effectiveness. The thickness was 12%, maximum camber was 0.00%, and the maximum thick position was 29.03%. So, here we are going to talk about the results and discussion of the yawing movement versus slight slip angle, which was validated using the MATLAB, the directional stability derivative, which is computed using the MATLAB, confirming the aircraft is statistically stable, the positive slope of the yawing movement versus the slight slip angle as shown in the graph. The graph indicates that the aircraft can generate a yawing movement to recover the slight slip directional stability of the Airbus A321-200 model. The plot shows the yawing moment versus the slight slip angle and the yaw rate versus the slight slip angle, illustrating the relationship between these parameters. The second graph therefore talks about which is easier for the pilot to understand the aircraft behavior during the crosswind conditions, which is essential for the safe landing. It helps us to understand how the aircraft behaves and different slight slip angle, which is critical for stability analysis. The third graph here talks about the simulation confirmed the benefits of the implementing the trimmable vertical stabilizer, which provided at a level of precision that allows for a level of precision for finer control under crosswind conditions, thereby improving the safety during critical flight phase like landing. The PID controller was successfully mitigated excessively deviation, maintaining the stability. In the fourth graph, we can see the system respond to sinusoidal disturbance. The oscillation and the anomalies of yaw rate, the graph shows how disturbance impact the aircraft stability. Stable aircraft quickly resumes their intended flying path and responds to disturbance with minimum delay when exposed to external stimuli. On the other hand, unstable aircraft could respond to disturbance by displaying observable oscillations of varying off course or varying off course. The last graph talks about during the crosswind during crosswind landing oscillations, the grab angle and the grab alignment. angle when mentioned as the function of time, the results confirm that the trimmable vertical stabilizer effectively reduces the grab angle, enabling more precision alignment with the runway, especially under crosswind conditions. Now, you may ask, what is grab angle? The grab angle are the long axis of the aircraft and the center line of the runway. So the both are aligned. So, and the alignment angle variation during the landing phase, the aircraft position along the runway was tracked to access the effect of crosswind on the lateral displacement. A paper outcome talks about to enhance the aircraft control movement, effective efficiency, maneuverability, and direction stability. The proposed TVS, Tunable Vertical Stabilizer, operates on a single system that permits a whole vertical tail movement. To investigate the control system to use design the Tunable Vertical Stabilizer using the traditional robust control techniques. We also apply the robust control algorithm to control the control system for the Tunable Vertical Stabilizer to enhance the maneuverability ability of the aircraft to be more stable with the new features. So friends, coming to the conclusion, this approach offers several advantages, including better aerodynamic performance, increased effectiveness, and improved maneuverability, particularly in challenging weather conditions such as strong crosswind or disturbance, and during complex flight maneuvers like sharp turn or sudden altitude changes. Further studies are recommended to investigate the investigation of the trimmable vertical stabilizer in more complex flight conditions, such as during asymmetric thrust scenarios and high altitude flights to understand the broader operation benefit better. Additionally, the development of real-time feedback system that can continuously optimize trim adjustment based on the flight condition is not just necessarily but urgent to fulfilling the leverage of advantages of this technology. Thank you everyone. Thank you members. And I would thank all the members who are joining this presentation. If there is any doubt or any questions, you can contact me. This is my email address. Thank you and have a pleasant day ahead.